Hello, today we're going to talk about cell potential under non-standard conditions. So far we've been looking at cell potential like this, which means that it's under standard conditions. For standard cell potential, our standard conditions are 1 molar solutions, 1 atm pressure, and 298 Kelvin. Now, in reality, we're probably not going to be at those conditions. So if you change the temperature, if you change the pressure, if you change the molarity, that cell potential is going to be different. There is an equation that we're going to use called the Nernst equation that will help us to see the difference between the standard cell potential and the real standard potential, or the real cell potential at these different conditions. So let's take a look at that equation. Here's the Nernst equation. We have our non-standard cell potential is equal to our standard cell potential minus RT over NF ln Q. Okay. So if we look at each part of this, it's non-standard, standard cell potentials. R is your constant, the 8.314. T is temperature in Kelvin. N is the moles of electrons involved in the process. F is Faraday's constant, 96,485. And Q is the same Q that we used back in Unit 7 to look at equilibrium. Let's review that part really quick. Let's say I have, reactants are going to products. If I write my equilibrium expression K, products will be on top, reactants on the bottom. When you calculate K, you always put in the equilibrium amounts, which for standard conditions will both be 1. So under standard conditions, K is 1. Right. Now let's say, for example, you have non-standard conditions, and you find that Q is greater than K. That means Q is too big. I have too many products. I need to make more reactants to get it to reach equilibrium. So it will shift to the left towards the reactants. And if we look at that mathematically, if Q is larger than 1, okay, then this whole term will be a positive value, and so it will be less than the standard potential, which makes sense because you're shifting in the reverse direction, so it won't produce as much of that voltage. Okay. Now, if we look at the other situation that could happen if Q is less than K. If Q is less than K, then I have too many reactants. I need to make more products to get it to reach K. So it will need to go to the right. It will need to go towards the products. Which means that because Q is too small, this fraction is less than 1, and so this term will be negative because of the natural log of that fraction. So when you're subtracting a negative, it's like adding a positive, and so your non-standard cell potential will be greater than your standard cell potential. And that makes sense because you're going towards the products, you're driving the forward reaction, so you're creating more of a potential difference. Right? So sometimes you might be asked to plug in values into the Nernst equation, although that's pretty rare for the AP exam. More common is they'll ask you to predict something like this using the value of Q. So if you can remember the shortcut here with Q, then that's great. Let me actually summarize this a little bit better. If it goes in the reverse direction, so your cell potential will be less than your standard cell potential, and for this scenario, your cell potential will be greater than your standard cell potential. So if you can remember that kind of pattern based on the size of Q, then you will be good for the Nernst equation most of the time. Okay, so the last kind of thing I want to look at here is concentration cells. So A concentration cell is when you have two half cells that are the same element or the same reaction going on. So a good example would be if I have one half cell might be copper 2 plus 2 electrons yields solid copper, and my other half cell, the reverse would be happening. So copper yields copper 2 plus 2 electrons. Now normally, if you did this at standard conditions and you were to hook those two things together with your wire and your salt bridge, you have to have the salt bridge, if they are the same molarity at standard conditions, nothing would happen. There's no difference between the two. But if you have different concentrations, you can produce a voltage between them. So let's say, for example, I have 2 molar concentration here and a 0.5 molar concentration here. Because I have a lower concentration on this side, the reaction is going to proceed towards the products. I need to create more ions here to increase this concentration to get it closer to equilibrium. So when I am writing out my value for Q, okay, it's always products over reactants, but we don't include solids, so those solids, coppers, don't matter. So we have our concentration of the copper ions in the 0.5 molar cell compared to the concentration of the copper ions in the 2 molar cell. So when I calculate Q there, I will get a fraction. In this case, it's 0.25. Oops. Which I can then plug into the Nernst equation if I knew the temperature, and then I'd have 2 moles of electrons in that process. And if I know the, if I look at the standard cell potential for this, standard cell potential, if all of this was at standard conditions, for a concentration cell, it's always 0. Because at standard conditions, they're the same molarity, so there's no potential difference between them. So you would just plug in 0 for the cell potential, standard cell potential, and you'd calculate Q based on the concentrations of the ions in the solution there. And that's how you would find the new cell potential. Okay, so in this presentation, we spent some time looking at the difference between standard cell potential and non-standard cell potential using the Nernst equation, L and Q. But we can relate our standard cell potential, our standard free energy change, let me do change in free energy, and then our equilibrium constant. When you have a positive standard cell potential, or like in a voltaic cell, then your delta G will be negative because it's spontaneous, it's thermodynamically favorable, there's no power source. And because of that, because we're looking at standard conditions, K will be greater than 1. Okay. Now, if your cell potential is negative, that means it's an electrolytic cell. It has to have a power source to make it work. And that means your delta G is positive. It's not thermodynamically favorable. You have to put in free energy. And then, since we're looking at standard conditions, K will be less than 1. It will favor the reactants. Finally, if I have 0 cell potential, and then I'll have 0 for the gives free energy, and K will be equal to 1. And again, this is for standard conditions. So if you're not at standard conditions where all of the molarities of everything is 1, your K values can be different and still be at equilibrium. But this is just for this scenario. Let's go ahead and review the equations that we can use to convert between these 3 things. You can go back and forth with delta G standard is equal to negative NFE for standard conditions. So that's one of them. The other equation, you can go back and forth with delta G. Delta G equals negative RTL and K. To go back and forth with free energy and equilibrium constant. And then if you were to rearrange these 2 equations so that I just want to look at standard cell potential and equilibrium constant, I can rearrange them to get rid of the delta G and solve for the standard cell potential is equal to RT over NF lnk. So that's how you would get that standard cell potential from the equilibrium constant. It's fine though if you'd rather just take the cell potential, find delta G, and then plug it into the other equation, because these two are on your formula sheet. Okay, so here's an example. We have a thermodynamically spontaneous cell. So that means delta G is negative and our standard cell potential is positive. Okay, I do like to annotate questions like this as I'm reading it. Now we have 100 milliliters of 1 molar iron 2 plus ions and 100 milliliters of 1 molar manganese 2 plus ions with a manganese electrode. So it's an iron manganese voltaic cell. Beakers are connected with a porous disc, so that's our salt bridge essentially, and the electrodes are connected with a wire. And we have a voltmeter measuring the voltage, no power source, which makes sense. Positive cell potential, we're good. Okay, qualitatively describe the effect on the value of Q and the voltage when the following changes occur. Okay, if I add some of this iron 2 nitrate in, if I'm adding iron 2 nitrate, nitrates are completely soluble. So essentially I am increasing the Fe2 plus concentration. So if I have more of the Fe2 plus concentration, remember that Q is products over reactants, I'm increasing the amount of reactants. Okay? That is going to make Q too small because we're increasing the denominator. In order to reach equilibrium again, we need to proceed in the forward direction. So that is going to increase the cell potential. So your non-standard cell potential will be greater than 0.74. Okay, let's look at B. If I have 100 milliliters of distilled water is added just to the iron beaker. So by adding water, I am decreasing the molarity of the Fe2 plus ions. Okay, again, if we're looking at products over reactants, I am decreasing the amount of reactants, which will increase the size of Q overall. That means Q is too big. In order to reach equilibrium, it needs to go in the reverse direction. That means that our non-standard cell potential will be less than 0.74. Finally, if we add 100 milliliters of distilled water is added to both beakers, there will be no change. Again, because it's products over reactants, it will decrease both the manganese 2 plus ions and the iron 2 plus ions. But Q is products over reactants. So both of those will decrease, but because you're adding the same amount of water to both, it's going to decrease it by the same proportion. So Q will stay the same, and there will be no change in Q, and there would therefore be no change in the cell potential. It's 0.74. Okay, so now we have a concentration cell, and we have zinc ions in both of them and zinc metal in both of them. But on the left beaker, we have 1 molar concentration, and in the right beaker, we have a 2 molar concentration. Okay, so that means that this beaker must be decreasing in concentration in order to reach equilibrium. So that means we must be going from zinc. We must be going from the zinc 2 plus ions to solid zinc in order to decrease the concentration. This one is smaller concentration, so we must be increasing its concentration in order to reach equilibrium. So it will look like this. So it says calculate the cell potential when the right beaker is filled with 2 molar concentration. In this scenario then, it's products over reactants. Well, the solid part doesn't matter, but the ions do. So I have the 1 molar ions on our product side. And then for our reactants, I have the 2 molar zinc 2+ ions, and the solid zinc doesn't matter. So my value for Q is 0.5. Then it says to calculate the cell potential, so I need to use the Nernst equation. I'm running out of space. So you would say the non-standard cell potential is equal to the standard cell potential. Okay, well I have 2 of the same cells, essentially 2 of the same half cells connected to each other, and at standard conditions they would both be 1 molar. So my cell potential would be negative 0.76 plus positive 0.76, which would cancel out to 0. So concentration cells will always have a standard cell potential of 0. And then you do RT, so 8.314, times our temperature in Kelvin, which is 298, over NF. N is the number of moles of electrons involved, and F is Faraday's constant, 96,485, times ln of Q, or ln of 0.5, which we calculated. Sorry, I had to cram that in there. So you would do, I always do the natural log first, natural log of 0.5, which would give us a negative value, and then times 8.314 times 298 divided by 2 divided by 96,485. And because we're subtracting that negative value, it winds up being a positive value, but it is quite small, 0.0089 volts for part A there. Then it says identify the cathode and nano and draw an arrow to represent the flow of electrons. So we already wrote our half reactions here. The zinc on the left is losing its electrons, so this is oxidation. The zinc on the right is gaining electrons, so it must be reduction. Oxidation happens at the anode, reduction happens at the cathode, and electrons always travel from the anode to the cathode, so electrons are traveling in this direction, and our potential in our voltmeter is 0.0084. Until it reaches equal concentrations, and then it will be at standard conditions, which would make it 0 potential again.